Hey friends, apologies for getting this out a little bit late, but as you can see, I'm trapped on the moon and have had to build a dome and generate oxygen, things like that. So this is a video for Calc 3. It is concerning the notion of integrals in spherical coordinates. So we've already looked at the notion of doing triple integrals. So we know the idea that's going on there. And the main thing here is, what do we do different when we have spherical coordinates as opposed to rectangular coordinates, or as opposed to cylindrical coordinates, which we have also looked at. All right. A lot of what we'll concentrate on this is going to be setting up the integrals. And once you have set up the integrals, it'll be kind of referenced back to things you've done before about being able to actually do the integration. Okay. Worst case, turn to Symbolab and see what the answer should be. Okay, so, all right, I'm going to share screen here, or I shouldn't jinx it like that. I am going to attempt to share screen, and it looks like it's going to work. Yay! So, integration in spherical coordinates. So the two things that we really have to get here is, first of all, that you're going to be replacing dv not with dx dy dz or with rdr or r dz dr d theta. Okay, we've already run into with cylindrical coordinates that sometimes the dv will have a little bit of extra term in it, and that can that can be a little bit hard to keep in mind what's happening. However, with cylindrical coordinates, we're able to justify what's going on geometrically, right? So what we're going to have to do here for spherical coordinates is to just say, this is dv, all right? When we talk about change of variables in general, we're going to be able to see why dv turns out to be this weird expression. Don may be able to give this to you in a geometrical sort of argument, but when I've tried to do that for spherical, it just doesn't, it's not as neatly thought out as the way it turns out for cylindrical coordinates. So anyway, so that's what we're going to have to deal with. Anytime it says dv, go ahead and replace it with this. If you had an integral that was in spherical coordinates that you had to convert to rectangular coordinates, that would mean you have to divide this thing out before making the conversion, all right? But as I say, a lot of what we're going to concentrate on these is going to actually be just how do you set up these darned integrals? And that is then why we have the motivation here for some of this integration in the different coordinate systems. If you wanted to do an integral where the region in question was a sphere, guess what? Spherical coordinates totally made for that. It works out super nice, okay? Then also, if we're talking about things that are like cones, those are also really pretty easy, okay? Because of the fact that your phi is just an angle from the North Pole down to wherever you are in this cone. So those are pretty easy to set up in that regard. But if you've got a flat top to them, it gets a little bit more challenging. We'll see this in an example here in just a second. Now, on the other hand, if you are talking about a cylinder, you should use cylindrical coordinates because, you know, it's cylindrical coordinates are set up for this, and it's really easy. If you do it instead in spherical coordinates, we'll look at that as an example, but you end up having to cut the top cone out and then do the integration over the cone and then do the integration over everything that's not in the cone. It's kind of a mess, you know. All right, on another hand, if you are doing a rectangular box, holy smokes, do not do that in spherical. It is super hard because in addition to having to deal with flat surfaces on the top, like we've got for that cone there. Now that flat surface on the top has square corners to it. And so instead of just having to say something like z equals 1, and then that's rho cosine phi equals 1, and you'd solve for rho and have rho equals secant of phi. Now you have to do that, but then you also have to limit your phi in terms of your theta and stuff. And holy smokes, just if you've got a rectangular region, just do it in rectangular coordinates. It's totally going to be worth any additional integration you have to do. So, all right, so for a quick example here, I want us to compare the setups that we have for a problem where we're asked to find the volume of a sphere, and the radius we're going to give is a capital R, and I just say capital R because when we talked about cylindrical, little r needs to be the variable, you know? So, all right. So if we were doing that in rectangular coordinates here, we know we would take an integral that went up through the region like that. I said integral, I meant an arrow that goes up through the region. And we would record the bottom and the top to be those z coordinates. And that's the plus and the minus of the square root. And then we would project it into a plane. And I probably should have drawn a quick picture for that here. So we draw it in a plane, and we think about drawing an arrow up in the y direction. And that then gets us the minus square root and the plus square root. Oh, shoot. Forgive me, folks. I am going to do a quick edit here because I wrote y squared when I meant to write x squared. And then I wrote it in green, and I don't like that. All right, so x squared, there, fixed, okay? So then I'm sure you totally expect me at that point to go ahead and do all of that crazy integration and stuff. And I believe we've done one along these lines before as an example. And the thing that's happening is that when you do the first integration here, the dz, then you're going to have 2 times that square root. And for that square root, you're going to have to either do a trig sub or look it up in a table, and you'll get something with powers, with 1/2 powers of the quantity r squared minus x squared. And then you'll have to integrate dy, and you'll have to have those powers again. And then finally, I think you'll end up having something relatively nice for the dx part of it, okay? But the point is the integration is totally nasty. You got to do a trig sub. Nobody likes trig subs. Okay, I kind of like trig subs, but not just doing them. I think they're a neat structure to them. So if we were doing this in cylindrical coordinates, on the other hand, then we would have to think not about dz dy dx, but r dz dr d theta. And that idea that we had previously about going up through the region and getting our z integration, that still holds. And so all we really have to do is to substitute in and have the little r squared appearing in there. Then the dr, you think about starting at the origin and going out. You enter the region at little r equals 0, and you exit at little r equal big R. So the integration there is nice. This is, in fact, the format of integration that would be a rectangle in rectangular coordinates. So in a sense, we're thinking about what's a rectangle in my different coordinate systems. And the rectangles in cylindrical will be cylinders, okay? So then for spherical coordinates, on the other hand, the things that are rectangles in spherical coordinates will have these constant coefficients here. And so you think about starting at the origin and going outward until you hit the edge of the sphere. And so you will be going from 0 to the radius of the sphere. Then you have to think about your phi. Now, phi equals 0 starts at the top and it rotates down until you get to the bottom. So going from the North Pole to the South Pole, if you're thinking about a globe. And of course, that's going to be a 180-degree shift, or in other words, going from 0 to pi. Okay. I know that's super confusing because you kind of want 0 to be at the equator because that's what you looked at on globes for your whole life. But it's just not how things are set up in this particular coordinate system. Okay. All right, then the last bit is the fact that you have to think about doing a rotation there around the z-axis, and it's the entire rotation from 0 to 2 pi for our thetas. And the nice thing in this is there's no thetas anywhere. So that means you can pull out the integral 0 to 2 pi d theta and just integrate that. And that's where we get this 2 pi from. The other part is factorable, and we're looking at integrating over essentially, a rectangular kind of thing with constant coefficients, not constant coefficients, constant limits. So consequently, we're able to factor out and say integral 0 to pi of sine phi d phi, okay? And of course, the integral of sine is minus cosine, and you substitute in, and that integral turns out to be 2. And then you have to have the last piece, which is the rho squared d rho, the integral from 0 to r, which is going to be just the 1/3 r squared. I'm sorry, 1/3 r cubed. And then when you put those all together, 4/3 pi r cubed, which is exactly the formula that you learned in the 4th grade. Okay, so not a big surprise, but it is nice to know where things come from. The comment was made one day about some problem we had in class of, is that really calculus? Yeah, it's geometry. You just use a formula from geometry. But the geometric formula came from the ancient Greeks. The ancient Greeks did something called the method of exhaustion. It essentially was calculus, but they didn't have the formality to it. The Greeks were really, really kind of picky about what they accepted as logic and stuff. And so that method of exhaustion thing that I referred to, that wasn't entirely accepted by all Greek mathematicians. So they knew these things, but they weren't super clear on them. Just like they knew the Earth was round, but when they calculated the actual circumference of the Earth and stuff, they made little errors in their calculation. Actually, the big one that you might read about in a history book, they made 2 large errors that canceled out, and they got almost exactly the correct answer. So don't ever let anybody tell you that that Columbus discovered the world was round. People knew that in the before the Common Era even. So, all right, let's jump back here and. Okay. So the next one we're going to take a look at is finding the volume of a cone. Now, we did this in cylindrical coordinates already. It wasn't too bad, but in that particular instance, we went ahead and drew our cone or the other way around. I started to say upside down. Really, this is upside down here, right? But for the setup of this, we can see that we have this kind of a radial symmetry there. Maybe it's azimuthal or something, azimuthal. But that symmetry means that we're just going to integrate 0 to 2 pi here on the outside with regard to the d theta. So we don't really have to worry about that portion of it. However, if we start at the origin and go out, okay, so that is doing our d rho integration first. Sorry, my arrow is a little bit crooked. But as we do that there, we enter the region where a rho is equal to 0. And we exit the region, and of course took my picture away. But we exit the region up here where we've got the z equal to h for the height, okay? So for that z equals h for the height, then we're going to do the conversion and say z is rho cosine phi. And so rho cosine phi equals h, and we solve and get h divided by cosine, which is h times secant phi. So that's where we get that portion there. Then with regard to our phi, we have to take a look and see that we are rotating down here from the North Pole down to whatever that darned angle is. And to figure out that angle, we've got to kind of come along here and say that we've got a radius of r and we've got a height of h. And so we can set up a right triangle and say that the tangent of phi is going to be that r over h. And so once you know that, then of course you can take the inverse tangent. And so we're going to say that our phi goes from 0 down to inverse tangent of capital R over h, okay? So now we've got the whole thing set up, and it's just a matter of doing the actual integration, which it seems like might be somewhat fearsome. But we already talked about that the theta is no problem. That's the rotation, and we've got that nice symmetry, so we can just factor that out. I said that we've got that nice symmetry. What I mean is there was no theta, which makes it super duper symmetric. I don't think that's a technical term, by the way. In any case, though, yeah. So that integral 0 to 2 pi d theta goes in there. And then I went ahead here and got 1/3 rho cubed, and I left the sine phi hanging on there. And we've got to evaluate from 0 to h secant phi. And then after that's done, we're going to do an integral d phi, all right? So this integral got us the 2 pi, and this 1/3 will just factor out to the front. And then we've got this rho cubed, and we're putting in h secant phi. And now the way I wrote this is probably, I did it this way to save space, okay? When I plugged in the rho cubed and plugged in the h secant phi, I went ahead and put the h to be cubed. But then the secant cubed, I took 2 of them and put them into the phi, and then I put one of them under the sine so that it's sine over cosine and made a tangent, all right? The reason I did that is to make the next step easier. So at this next step here, you can let u be tangent phi, and then du is secant squared d phi. And so you end up with a 1/2, and I didn't write that. Yeah, I should have written that as a separate step. A 1/2 tangent squared phi, okay? If, on the other hand, you had broken it differently, you could have done something with a secant tangent or something, but I knew how it was going to turn out, and so I tried to make it nice, okay? Because now we're going to take the tangent of the inverse tangent, bam, just cancels out. And so consequently here, in this next step, we've got the 2 pi over 3 times the 1/2, that's where pi over 3 comes in. We've got an h cubed, which we don't want, right? Because we're only supposed to have one factor of h in this. But we have an h cubed showing up here, and now we have the square of the tangent of the inverse tangent. So that means we're just going to have r over h quantity squared. And lo and behold, it cancels out all but one of our h's, and we end up with an r squared, and that's exactly the formula that, again, I don't remember for sure, but I think that this may have shown up as early as 4th grade, okay? So I think it's neat to know where these things came from. Now, one thing about this is that these are common regions that you might have to integrate something over at some point. So, you know, pay attention to how those limits went, right? And also pay attention that the setup is more important than the integration, because the setup is really the new part when it comes to an exhibit. when it comes to an exam, we can't ask you to do huge amounts of work. It has to be something you can finish in a short amount of time. Okay. All right, so this problem is here to give us contrast and to show that you don't always want to do everything in spherical coordinates. So this one asks us to find the volume of cylinder with a radius of capital R and a height of H. So in cylindrical coordinates, since it's a complete circle there, you're going to have the 0 to 2 pi. Since it is going out from the z-axis to the surface of the cylinder, you're going to have 0 to r, 0 to capital R on your r limits. And then the height of it's just going to go 0 to h because the top and bottom are both flat. So your integration is easy to set up, and you get r dz dr d theta. And I skipped all the hard work here, okay? But you're integrating just d theta 0 to 2 pi, no problem. You're integrating dz 0 to h, no problem. And you're integrating r dr from 0 to capital R, so you have 1/2 r squared, and you plug in, and you end up with pi r squared h, which is totally the answer, again, that you knew in 4th grade. So, all right, but in spherical coordinates, on the other hand, if you want to do this cylinder here, you need to first of all carve out the cone, which we already did in the previous example. And then you have to think about what happens as your phi goes from that inverse tangent of r over h down to the equator, which is, I wrote down pi, and that's supposed to say pi over 2, okay? So then in figuring out what's going on with that, you think about it starts at the origin. We did this on the previous one. It starts at the origin and it goes outward until it hits the surface that you got. But now, and now that did the cone portion. Now we've got to think about when we are instead on this portion that's outside of the cone, that we start at the origin and we go out to that surface there. Well, that surface is not going to be given to us by z equals h, but rather little r equals big R, right? And little r is rho sine phi equals big R. So that means that rho is going to be equal to big R cosecant of phi. And that is the reason why we've got our rho squared d rho going from 0 to r cosecant phi. Okay, I'm not going to do the integration on this. You could, if you needed to, turn to Symbolab to check your answer on this, but you do know what the answer should turn out to be at the end, right? So anyway, I'm going to beg off on that one and try to take a look at just one more example here, okay? I like this example, even though it's kind of evil. Take a look here. Example 4, we're asked to evaluate 1 over x squared plus y squared plus z squared across a region, which is a ball with a radius of 1 centered at the origin, okay? So that means at that point of the origin, this function's not defined, but it is defined everywhere except for that point. And we can actually get it taken care of in a limit. Now, I have not bothered to do the portion here of writing down an a and taking the limit as a goes to 0, which is totally what I'm supposed to do as a good calc teacher and stuff. But we always skip over that portion, okay? The bizarre thing here is we have something at the origin that's going to infinity. And when we integrate it, we don't get infinity. Super weird. But the thing that's going on is when you convert this into spherical, you get 1 over rho squared. And because dv had rho squared sine phi in it, bam, those cancel out. So now we really only have to integrate the sine phi. And because our region is a rectangle in spherical coordinates, all of these constant limits of integration mean we can just do 3 integrals. The integral 0 to 2 pi of d phi, 2 pi. The integral from 0 to 1 of the d rho, that's going to just be just be 1, right? The integral, though, 0 to pi of sine phi d phi, we did that in an earlier problem, and it turns out to be what? Negative cosecant phi, and then you plug in, and the negatives cancel some stuff out, and it ends up being 2. So the answer on this turns out to be 4 pi, which is bizarre that we should get a finite answer out of something that has an infinity hidden in it. But if you look back to your examples from Calc 2, hopefully your teacher will have done a few examples like Gabriel's horn, which is a figure that has a finite area under it. Well, I'm sorry, it is something where you do a rotation about the x-axis, and the volume you get is finite, but the surface area on the outside is infinite. So that's like a super weird little paradoxical kind of thing. But these sorts of things show up a little bit, and it has to do with limits at infinity. They act a little bit weird sometimes. Okay. All right. I'm going to let it go at that. I'll see you in class.